Again, I'm going to work on these review problems while the projector warms up. And this is section 2.8. We're going to be doing three things. We want to review these domain of functions first. Because when we're doing some of these problems in section 2.8, they're going to ask you for the domain of the function. You have to be able to say what it is. Alright. So this first function, f of x, is equal to 3x minus 7 over x plus 3. F of x is equal to 3x minus 7 over x plus 3. Now, if we recall, when we're talking about domain, with our domain, we need to look at whether something is a fraction, a square root, or both. So you're looking at whether something is a fraction, a square root, or both. Now, if we look at this number 1 problem here, this number 1 problem contains no square roots, but it is a fraction. Now, when we're talking about fractions, what's my criteria for fractions? If I'm talking about excluding a number from the domain,
The bottom can't be 0.
the bottom can't be 0. So for this x plus 3, this denominator cannot equal 0. And if I solve this x plus 3 cannot equal 0 for x, I'm saying that I need to eliminate negative 3 from that domain. So for this one, I'm eliminating anything that would make this denominator 0. So in this case, a negative 3. So I'm excluding negative 3 from that domain. Now, if I write negative 3 on a number line here, and I cannot equal negative 3, so I can put an open circle or a set of parentheses here. I can have every number smaller than negative 3 and bigger than negative 3, but just not negative 3 itself. So my domain for this function would be negative infinity to negative 3. I'm going to put a parentheses there because I'm not including that. Or negative 3 to infinity. So I have every number except negative 3. So this is my criteria for a fraction. Your denominator cannot equal 0. Alright, let's look at number 2. Number 2, I have f of x is equal to the square root of x minus 7. F of x is equal to the square root of x minus 7. This one isn't a fraction, but it is a square root. Now, do you recall our criteria for square root? Can my square root equal 0?
Yes.
Yeah, I can get a square root of 0.
Can't be negative.
It can't be negative because we don't want to deal with any imaginary numbers. So, if it can't be negative, but it can equal 0, this square root needs to be greater than or equal to 0. So if x minus 7 is greater than or equal to 0, my x needs to be greater than or equal to 7. Because again, I can have 7 here, because that'll give me a square root of 0, which is 0. I can do that. Or I need numbers bigger than 7, like 8, 9, 10, because that'll give me positive numbers underneath the square root. I cannot have negative numbers because, again, let's say I had a number less than 7, like 6. If I plugged in 6 here, this would be 6 minus 7, which would give me a square root of a negative 1, which is I. And we don't deal with imaginaries when we're talking about domain. We're only looking at real numbers. So I'm excluding anything that will make my square root negative. But in this case, I can actually be 0, because I can get the square root of 0 just fine. So if I'm looking at this one, I need numbers that are greater than or equal to 7. So that's a bracket all the way to infinity. So this is my domain for 2. So I'm including that 7 and also numbers bigger than 7. Okay, let's look at 3. Alright, this one. It has a square root. And what else is it?
Fraction.
Yeah, it's a combination of both, square root and fraction. Now, since this is a combination of both, my domain will be a combination of both. We know we cannot equal 0 at the bottom, and we know that my square root needs to be positive. Now, if we're looking at this one, if I take the square root of x minus 7 and place it in the bottom of my fraction, what's going to change in this domain? Can I equal 7 over here? No. So this one exactly cannot equal 0, because again, fractions cannot equal 0. So I'm going to take my x minus 7, but this time we're just going to be greater than 0, not equal to 0. But greater than 0. Because again, I cannot equal 0 here because I can't get a 0 in my denominator. So the only thing that changes here is that my x needs to be greater than 7, but now I have a parentheses on the 7 as opposed to a bracket. It's the only thing that changed there. Just because we can't equal 7 here, because it'll give me a 0 at the bottom. So we have three things. Denominators, square roots, and then a combination of both. Now we did this in lesson something or another. I can't remember. It's been several lessons ago probably. Alright, so keep this information handy, because we're going to be using it for this upcoming section 2.8. Because your 2.8 is basically combining more than one function. These are objectives here. We're talking about performing operations on functions. Sounds like you're like taking a function to a hospital or something and operating on it. But really, when we're talking about operations, we mean adding, subtracting, multiplying, and dividing between two functions. So let's look at that. Let's say I have some function yellow. This is my yellow function. Let's call it y of x. And now we're going to perform some operation. Again, that's either I'm adding or subtracting or multiplying or dividing another function. Let's call that function b for blue. Let's call this a b of x function. So we have one function performing some operation with another function to get a new function. We call it green. to get a new function that's a combination of the two. So I have one function performing an operation with another function, and this new function is a combination of the first two. Now, each of these functions have restrictions on domains. So I have a restriction on domain for y, which is this yellow function. This one has a restriction on domain of this blue of x function. The g of x function would be a combination of these. So if I have a restriction here and a restriction here, this g of x function, you need to take into the restrictions of both. Because if I started out with a restriction here and a restriction here, when I made a new function, those restrictions don't disappear. They just become involved with the new function. So again, later on when we start combining these functions, we'll have to state what the domain is of the new function, which would be in consideration of the first two. I don't know if that makes sense, kind of. And of course, it'll be something other than colors. It'll be like numbers and stuff. But this is kind of what we're doing. Two functions making one. Alrighty. Let's look at example 1. They give us the function f of x is equal to 25 minus x squared. And then g of x is equal to 5. And for our question, they want us to add f plus g of x. So we're looking to add the f function plus the g function. And this is example 1 in your book, which is on page 262. Now this f plus g function, you could also write this as f of x plus g of x if you wanted to. They're basically telling you to take your f of x function and then add your g of x function. That's all you do there. So my f of x function is 25 minus x squared, and I'm going to add my g function. And technically, that's all I can do with that problem. I mean, they're not like terms, so I can't do anything else with it. Now, you can evaluate these functions at a particular number. Let's say we evaluated this function at 4. If I wanted to evaluate this function at 4, and actually I wouldn't write it like this. I want this f plus g function evaluated at 4, not just my f function. Alright, so we got these two functions, we added them together. If I wanted to evaluate these two functions added together at 4, technically what I can do is add my f function at 4 plus my g function at 4. Or you can go ahead and do f plus g and then plug in a 4 for this equation. We can do this two different ways. We can do f plus g to get this answer and then plug in a 4 here. Or we can do f of 4 and then f of g and then combine the answers. Either way is fine. So if I get f of 4, I'm going to plug in 4 for x in this f function. That's the square root of 25 minus 4 squared. And then g of 4. If I look at this g function, what's g of 4? Yeah, it's just 5. No matter what I plug in here, in the g function, it will be 5. So when we simplify this is 25 minus, what's 4 squared? 16. So it's 25 minus 16. And the square root of 9 is 3. So this function, evaluated at 4, is 8. Or like I said, I could have just added them together and then plugged in a 4 at the end. Alright, so let's look at that on a graph. Alright, so if you look at this function here, the functions that are black are two separate functions. So this semicircle is the square root function, and this straight line here is our constant function 5. The blue is the two functions added together. So you see how this blue function took on the characteristics of the other two. Now if we're evaluating the function, so I told you to evaluate the function at 4. This semicircle, which is the f function, evaluated at 4. So when my x is 4, my y is 3, which is what we have here. The g function evaluated at 4. When my x is 4, the y is 5, which is here. This blue function is them added together. So this is 3 plus the 5 to come up here to the 8. So that is all the function is doing. You have this one plus this one to give me this one. If it was subtracting, then you would subtract. But you can look at this clearly on the graph. I'm here at 3, here at 5. 3 plus 5 will take me to 8 for the blue function. And this is your figure 2.38 or 2-38 in the bottom of page 262 here. So if I'm looking at this graph, what if I wanted to evaluate this function at 3? We can take these two functions. So at 3, this semicircle is at 4. And my g of x function is once again at 5. So this blue function should be where? 9. At 3. At 9, which it is. So sometimes you might see something like that, well, where maybe they won't give you the blue circle, but they'll give you these two functions, and then maybe they'll ask you what the point should be. And you can look at the graph and just add them. This one is at 3 plus 5, so this one should be at 8. If I'm evaluating at 3, I have 4 plus 5, and this one is up here at 9. Questions on that? Just adding two functions together. Just literally adding them and simplifying, and you can also evaluate them at a particular number. Anybody lost on that? You can also put this in your calculator and look at the table. All right. All right, so let's keep going here. Let's look at example 2. So example 2 says evaluate functions for given values of x, And this is page 263. And if m of x is equal to 4x, n of x is equal to the absolute value of x minus 3, and then p of x is equal to 1 over x plus 1. So A, m minus n, and let's evaluate that at negative 2. B, m times p, evaluated at 1, and C, p divided by n, evaluated at 3. So our first example was the addition. These are other operations: subtraction, multiplying, and dividing. Now, for A here, I can do this two different ways. I can go ahead and write m minus n and then plug in a negative 2, or I can plug in a negative 2 in my m function, then plug in a negative 2 in my n function, and then subtract those two answers. Either way is fine. So m of x minus n of x, that is 4x minus the absolute value of x minus 3. So technically m minus n is just this. Now if I wanted to evaluate this at negative 2, I can plug in a negative 2 here. And I'm just plugging a negative 2 wherever I have an x. So this is 4 times negative 2. Now, negative 2 minus 3 is what? It's negative 5. What is the absolute value of negative 5? 5. And negative 8 minus 5, negative 13. So if I wanted to, I can do the problem like this. F of x, why am I calling it f? Well, there's no f up here. M minus n, and then plug in a negative 2. Or I can do m of negative 2 minus n of negative 2, and then solve the problem that way. So just maybe start plugging them in the very beginning. So m of negative 2 is 4 times negative 2, which is that negative 8. And then n of negative 2 is negative 2 minus 3, absolute value. That's negative 5, and the absolute value of it is 5. And then I can subtract these two answers. So I can do it this way as well. Either way is fine. A lot of times students like to do it separately because sometimes when you perform an operation you get some kind of wonky looking functions. So it might be best to kind of do them separately and then perform the operation. But again, you should get the same answer regardless. Alright, let's look at B. M times P evaluated at 1. M times P evaluated at 1. Alright, so my M function is 4x, and my P function is 1 over x plus 1. So you're just multiplying these. So that's 4x over x plus 1. And if I wanted to evaluate this at 1, I can just plug in a 1 for my x value. So this is 4 over 2, which is just 2. And then for C, I'm taking my P function and dividing it by my N function. And then we're evaluating this one at 3. Alright, so this becomes 1 over 4 divided by 3 minus 3. And the absolute value of 0 is, now, what's going on with this problem?
0 in the denominator.
I have a 0 in the denominator. So this is undefined. This problem is undefined at the x value 3. Because that denominator cannot equal 0. Now let's look further into depth into this C part here. If I go back to this original function, this P divided by N of X. We already know at 3 this function is undefined. So if we're looking to take the domain of this function, I know that I'm going to exclude 3 here because this 3 will make me have a 0 in the denominator. Because again, if we go back to our review, our functions that are fractions cannot have a 0 at the bottom. So this one cannot equal 0. And then when I solve this one, I get x cannot equal 3. Which we've established here, because if we do, we'll get a 0 down here. Now looking at this problem, isn't this x plus 1 also a denominator? Yeah. So this one also cannot equal 0. So we said that x cannot equal 3, and it also cannot equal what? Negative 1. And this is what I mean by when you have two fractions, you have to take into consideration, not two fractions, two functions. You have to take into consideration the domain of both of them when you're combining them into one function. So for this one, I cannot have a negative 1. Again, it'll give me a 0 in the bottom of a fraction. But I also cannot have a positive 3. It will give me a 0 in the bottom of a fraction. So this domain needs to exclude 3 and negative 1. So let's write that out. Let's put this on a number line. Negative 1 is smaller than 3. And I know I am excluding both of those, so I just put an open circle or parentheses on those. Now let's test these 3 intervals. The interval less than negative 1, the interval in between negative 1 and 3, and then the interval greater than 3. Give me a number that's less than negative 1. Yeah, I can do negative 2. It really doesn't matter. Now, let's test negative 2 in this function. If I plug in a negative 2 here, will they give me a 0 at the bottom? No. Can I plug in a negative 2 in this absolute value?
Yes.
Yeah. So I can actually use this interval here. Give me a number in between negative 1 and 3. 1, you can use 1, 0, it doesn't matter. Now we can use 0 since 0 is usually easy to work with. If I plug in a 0 for x, will that do something to my problem that's undefined? Well, this is just 1 over 1, which is 1. Absolute value negative 3, which is 3. So no, this 0 won't harm our problem any kind of way, so I can use 0. Give me a number greater than 3. You can do 5, it again doesn't matter. If I plug in a 5, will it give me any type of restriction on my domain? No. So I can actually use all 3 of these intervals. I'm just not using negative 1 and 3. So that means for my domain, I can have numbers smaller than negative 1, but my negative 1 needs a parentheses. Or I can have numbers in between negative 1 and 3, both of them with parentheses. Or I can have numbers greater than 3. So I actually need all 3 of these intervals here. Because again, the only thing that's being excluded is this negative 1 and the 3. Now if we tested some numbers here and it turns out that we couldn't use them, then we would have to eliminate that interval. But in this case, the numbers we tested were fine. So I'm only eliminating these numbers here. And this shows you why it's undefined at 3. Because again, it's a parentheses. It gives me a 0 in the bottom of my denominator. And technically they could have asked the same question for a negative 1, because negative 1 will also give me a 0 in a denominator. So again, we're going to be testing the domain of these new functions that we get. Excuse me. Alright, so let's look at the skill practice 2. And let's look at skill practice 2C. And we're using the same P and M functions. So this time let's do P divided by M divided by 0. Not the P divided by M evaluated at 0, not divided by 0. That wouldn't work. And then let's find the domain of P divided by M of X. So let's find the domain of this one. So let's evaluate P divided by M at 0. So 2 different things. So let's evaluate this at 0, and let's find the domain of the P divided by M function. It's again the same P and M that was in the example. Alright, So this p divided by m. I take my p function, which is 1 over x plus 1, divided by my m function, which is 4x. So 1 over x plus 1 divided by 4x. And I'm going to evaluate this at 0, meaning I'm going to plug in a 0 wherever I have an x value. So 1 over 1 is just 1. But if I plug in a 0 down here, this will give me a 1 over 0, which will make this function evaluated at 0 what? Undefined. So when I come over here to evaluate my domain, I know that I'm going to have to exclude 0 from that domain. What else am I excluding? The negative 1. So I can't equal 0 at either one of these denominators. So x cannot equal negative 1, and x cannot equal 0. Alright. Can I plug in numbers less than negative 1?
Yes.
Yeah. What's the number between negative 1 and 0?
Negative 1/2.
Yeah, like a negative half. Can I plug in those? Yeah. And a number greater than 0? 1. Can I plug in that?
Yep.
Yeah. So again, only thing I'm excluding are these two numbers here. So I can have numbers less than negative 1, numbers in between negative 1 and 0, and numbers greater than 0. So this will be my domain for C. Everything except negative 1 and 0. You also want to pay attention, see how this is kind of breaking it up into 3 separate parts. So you'd be testing 3 separate intervals. So like a negative 2, negative 1/2, or negative 0.5, and maybe positive 1 here. Alright, so that is C. Again, this is the operation division. Evaluated at a particular number. You can also get the domain of that function by figuring out what values need to be excluded from the domain. Put them on the number line and test different intervals. Alright, let's keep going. The next part of this lesson is dealing with the difference quotient. We will come back to that one at the end. Let's go to composing functions. And this is page 266. Your composition of functions, and they usually write it either f with this open circle g of x, or they write it like this, where you have some function that is composed of another function, hence the word composition. So basically, I'll take, what this is, the output of g of x becomes the input of f of x. So the output of g of x becomes the input of f of x. So it's a function within another function. So if we go back to our yellow and blue functions here, the algebra of functions means you have one function, you do a little something, and then get another function, and then it becomes a new function. Your composition function, basically, volume please. If I have this yellow function, and inside this yellow function is the blue function. And then I have my yellow function. So what's going to happen is that I'll have some x come into the blue function. And when that x comes into the blue function, it's going to do its thing. It's going to have some operations there, adding, subtracting, multiplying, dividing. And it's going to produce an output. And that output will go inside the yellow function. And this whole thing is actually the green function. So you have a function within another function to become another function. And this outside function will take on the characteristics of the blue function and also the yellow function. So I have some x value come inside the blue function. It'll do some operation here, and it'll spit out an output, and that output will be b of x. That will then go inside the yellow function to produce the green function, which would be g of x. So g of x is a combination of the b and y. And if I were to write that, g of x is equal to the y function that is comprised of, or composed of, the b function. Again, I have some blue function becomes the input of the y function, which is the green function. And that green function will have the characteristics of the blue and the yellow. Now, believe it or not, chances are you have kind of done something like this before. Even if you don't know you've done something like this before.
Algebra 2 in high school.
Yeah, Algebra 2. You've actually probably done this in real life. Just so you know you did it in real life. Now, let's think about going to the store. And you go to the store, let's say you're buying a shirt. That shirt has a discount and a tax. That shirt, let's say it is, I don't know, let's say we don't know how much it costs. Let's just call it X. But we do know that it is discounted 15%. And let's make that a decimal. 15%. 0.15. Now my discount, like I just can't go in and take 15 cents off something, right? Unless it's $1. My discount is usually depending on how much it costs. So technically, that is a function. And then my tax is depending on this one. And let's say the tax is 8% for whatever reason. 8% of whatever the shirt cost. If I want to calculate the final cost of this shirt, this final cost of the shirt, if I call this a function D, and this a function T, this final cost of the function depends on the tax, which depends on the discount. So again, technically, you've kind of done this before. Maybe you just didn't know it. Am I the only one that would like calculate this in a store? Am I alone? Who? Okay, raise your hand if you would actually like calculate a discount or something. Am I the only one? Okay, you would do that. You do that. Okay, so I'm not by myself on that.
Are you a good tipper?
Yeah, I'm a very good tipper. But yeah, I'm not alone with like calculating that. I just be careful with my money. So I'll just go and like, oh, it's a discount. Let me see how much that costs. I'm like,
I compare discounted items to the other bigger items because a lot of times they try and trick you.
Yeah.
You think you're getting this, like, wait a minute, price per unit's actually more expensive on the discount.
yes, price per unit. Like people don't realize that like if you're buying something that has 3 items in it, and you're buying something that has 10 items in it, the items that has 10 items in it is more, but the cost per unit could be cheaper. So you might be better off buying the one that's more expensive with the 10 items as opposed to the least expensive with the
It's always
3.
tricky, they put it at eye level, they put discount, and you're actually.
Yeah, like until you should pay attention to that stuff. Like you save some money. Like, just saying.
You're right, I've seen that.
Walmart's the worst.
Price per item, yeah.
Yeah, and I've noticed that they'll have a large quantity that it's more expensive per unit, pound, whatever.
Yeah, because I know when I had the flu and buying flu medicine, they'll give you like a packet of medicine is like 10 tablets in it or something. Like, good grief. You're better off buying it in bulk. All right.
Oh, the actual tax, though, it wouldn't be 0.08x, it'd be 0.08x minus it, or x minus point, or
No.
0.15x, correct?
Well, just if we're calculating just the tax, if we're doing the final cost, then we can be minus it out. Yeah. Yeah. So the cost minus the discount plus the tax. Yeah.
Will the tax be on the discounted price, not the normal price? Based on your math up there, that's what you'd be doing.
Yeah. So that's what I'm saying. If you're doing a final tax, we're going to have to do the final tax before we do the final cost. You're going to have to do this T function inside this D function inside the T function, if that makes sense. You're going to have to do this D function first, then apply the T function, and then calculate the final cost. So it's functions inside a function. And again, if you ever calculated a discount and tax, you have technically done a composition of a function. Maybe just didn't know you did a composition of a function. But yeah, your final cost, like if that shirt was $20, I mean 20 minus whatever's going on in the D function, whatever's going on in this T sub D function, or like added. I think this ended up being like $18.36. Be the final cost of the shirt. But yeah, so again, function inside of another function, or when you have one function depending on another function before you can actually figure out what the new function is. And again, the domain has to take into consideration both functions. Alright, so example 6 here. Let's look at this just with some letters and numbers, some algebraic expressions. So f of x is equal to x squared plus 2x. G of x is equal to x minus 4. Let's find f as a function of g. You can write it like this, or you can write it like this. Either one is fine. And again, this is not multiplication. You are saying that my f function becomes a function of the g function. My f function becomes a function of the g function. So whatever my g function is becomes the input of my f function. Now, let's go back and think about evaluating expressions. I have some f function. If I wanted to evaluate this f function at 6, this 6 is an x replacement, meaning that I'll take my x function, or my f function, excuse me, and everywhere I have an x, I'm replacing it with 6. This kind of works the same way. This one is telling me that I'm going to take my f function, this x squared plus 2x, and again, anything that's inside the parentheses is an x replacement. So I'm taking my f function and replacing my x values with g of x. So my f function, replacing all of my x values with g of x. Do you see what we did there? Well, what I did there? Again, whatever in this parentheses is an x replacement. So instead of x here, I'm replacing it with the g function. And my g function is x minus 4. So let's look at that again. I have my f function and my g function. F of g states, take your g function and replace your x value and your f function with the g function. So instead of x squared, I'll have x minus 4 squared plus 2 times x minus 4. So you're taking one function and putting it inside another function. Again, taking one function, putting it inside the other function. Now your book wants you to evaluate this new function at 6. So all that means is plug in a 6. So that's 4 plus 4, which is equal to 8. Now one thing you could have done is done this, but found g of 6 first. G of 6 would be 6 minus 4, which is 2. And then what do you think you can do with that 2 to plug it into the f function? Now you can find f of 2, which would be 2 squared plus 2 times 2 which is again 8. Two separate ways of doing that. But this is what I mean when you have an output of one function becoming the input of another function. So we got an answer, and then the answer we got, we use it for the other function. So an output became an input in the other function. So you can go ahead and do f of g of x first, and then plug in the number and simplify, or you can simplify the inside, and then take that number and bring it to the outside. You should get the same answer regardless. A lot of times it's easier actually to kind of do this one. Like do the inside first and then take that number to the outside function. Just because sometimes these functions can get a little crazy. So it might be better to keep them separated first. But again, it's up to you. Alright, so let's take this example and work on skill practice 6. And this is page 266. We're using the same example. And actually I want you to use the same functions, f and g. And the book told us, you know what, I cannot be bothered to make any new functions. Let's just use these same ones. So this time, let's do g of f. I don't know why I made that circle so big. So let's do g of f of x, but also let's do g of f, and then the question wanted us to do the number 10. So this is the g function composed of the f function. So let's try this one, the practice 6. Alright, so for this one, if my g function, which is composed of the function f, means you want to take your g function and replace your x value in your g function with f. Because again, the inside of the parentheses is an x replacement. If you want to, you can write it like this, g of f, to kind of get rid of like all these parentheses in here. This makes it a little bit more streamlined. So my g function, instead of x, I can do f minus 4. But my f is x squared plus 2x. So that's x squared plus 2x minus 4. So this may help you if you kind of, get it streamlined a little bit. Just call the functions f and g as opposed to f of x and g of x. Alright, if I want to evaluate this function at 10, I can plug in a 10 in this final function here, or I can do f of 10 first. So I'll take my f function and replace all of my x values with 10. So that gives me 100 plus 20, which is 120. And then I can take this 120 and plug it into the g function. So that's 120 minus 4, which is 116. So this is composition of functions. One function that's made up of another function. Alright, questions on this? I know a lot of students do find this a little confusing. They're trying to figure out whether,
Finds out where it starts.
yeah, like trying to figure out, okay, what goes where. But this one, like I've been telling students maybe to kind of write it like this, where, remember, inside the parentheses, it's replacing your x.
Right.
So instead of g of x, we'll have g of f, but my f is x squared plus 2x. So it might be easier to kind of just eliminate the x part and just do
You
gf.
just gotta think about which way it goes.
Yeah, it's kind of, you get like, wait a minute, am I doing my f function and putting g in it, or am I doing my g function and put f in it? So it gets kind of, but yeah, it goes with the one that's on the outside. So you're taking the g function and plugging in f. So it's the outside function. And again, when you're composing these functions, you still have to deal with the domain and range using our criteria, whether it's a fraction, square root, or some combination. Right, so let's look at example 8. Example 8 gives us m of x is equal to 1 over x minus 5. P of x is equal to the square root of x minus 2. And they want us to find m of p of x. And they want us to find the domain of this function. Now this m of p of x, you can rewrite this as m of p, if it helps you. So we're taking our m function and replacing all of our x's with p. But my p is the square root of x minus 2. And then minus 5. Now let's look at this.
Not a square root could be negative. Can a square root be negative?
Yeah, it can't be negative. This negative 5 is outside the square root.
Yeah.
It's just this minus 5 here. Now, let's look at this. From the very beginning, before we actually added in this p function, this was a fraction, right? My fraction cannot equal 0 in the denominator. So before I even put in this p, I know this p cannot be what?
5.
This p cannot be 5. So that's one part of it. And my p actually is square root of x minus 2. So I know that this square root of x minus 2 cannot equal 5. Now, let's square both sides of this to get rid of that square root. 5 squared, and then I'll add 2. So one part of this is saying my x cannot be 27. Now, once we put in this x, the square root of x minus 2, we still have a fraction, right? Now, we've got the fraction part. What about this square root? Isn't there a criteria for square roots?
Can't be imaginary.
It cannot be imaginary.
That's what that's.
Yeah. So this square root cannot be imaginary. So it needs to be greater than 0. Can this one equal 0?
Yes.
Yeah, this one can actually equal 0,
Even though it's under a fraction.
even though it's under a fraction, because if this was 0 down here, I still have this negative 5. If it didn't have that negative 5, then it couldn't equal 0. Again, we can square both sides. So now I have x needs to be greater than or equal to 2. So I got two different things going on here. I got x cannot equal 27, and I got x must be greater than or equal to 2. So let's think about that on a number line. I have 2, and then I have 27. Since I can't equal 27, let's make that an open circle. I can equal 2, however, so I'll make that a closed circle. Give me a number less than 2.
1.
1. So if I test 1,
You negative 1.
that'll be a negative 1 down there. So can I use this interval? No. So actually going to mark that interval off. Give me a number between 2 and 27. Alright, let's try 3. Can I plug in a 3 here?
Yes.
And be fine? Yeah, so we can use that one. Give me a number greater than 27.
28.
28. Can I use 28?
Yes.
Yeah. So this is the only interval that we're going to discard here. So I can use 2, so let's make that a bracket. All the way to 27. 27 needs a parentheses because I cannot equal 27. Or I can do 27 to infinity. And these require a little bit more thought. And you want to look at your domain each step of the way. When I started here, I had a fraction. So I need to say, okay, that p cannot be 5. What I plugged in what p was, I have another fraction, which we already took care of, down here, but now I have a square root that I need to figure out. So I have a fraction and a square root. So you need to take into account both. Alright, so that is it. 2.8, there's still a little bit more to go on it, so I'll probably end up pushing a day back. 2.8 is our last section in Chapter 2, so it means that we'll have a Chapter 2 test coming up. So what I'll do is I'll post Chapter 2 like I did Chapter 1. I'll post it today, but it won't be due until 2.8 is due.
Do you have any homework at the time it's due tonight?
Yeah, it's not there tonight.
2.8 was supposed to be due, I think, tonight, but we didn't finish it. 2.7 is probably due tonight. 2.7.
I think you have it due on the 18th or the 19th, right?
2.7. 2.8, I probably have to push it. But yeah, make sure you're looking for test 2. If you're ready to take test 2, you can go ahead and take it, but you don't have to until we finish 2.8. Let me stop it recording.